Okay, let's start. So the first thing I'm going to do is go over the exam, and then we will begin our study of group theory in earnest. Are there any questions before I start? So the grades were all posted yesterday on the exam, but I'll go over it right now. So problem 1. So we have the numbers 245 and 567, and we want to use the Euclidean algorithm to calculate the greatest common divisor. So we take 567 and we divide it by 245. It goes in 2 times, I think. Let's see, that's 490. So that leaves a remainder of 77. And then you take 245 and you divide it by 77. And this probably goes in 3 times. Let's see, 3 times 77 is 231. So I think that leaves a remainder of 14. 77 is 5 times 14, and that leaves a remainder of 7. 14 is 2 times 7, and that leaves a remainder of 0. So the last non-negative, the last positive remainder is 7. So the GCD of 245 and 567 is equal to 7. And then we want to use the Euclidean algorithm to write 7 as a linear combination of these 2 numbers. So we have 7 is 1 times 77 minus 5 times 14. But 14 is 245 minus 3 times 77. So this is equal to minus 5 times minus 3, 15 times 77 plus 1 times 77, 16 times 77 minus 5 times 245. And 77 is this minus this. So this is 16 times 567 minus 2 times 245 minus 5 times 245. So this is 16 times 567. 16 times 2 is 32. This is minus 32 minus 5 minus 37 times 2, 45. So if we want to write 7 in the form 245x plus 567y, what we get from the Euclidean algorithm is that x is minus 37 and y is 16. So that's the answer for part B. Okay. Any questions about this? Yes, no? Okay.
Professor?
Yeah.
Could you go over how you determined these 2 numbers again, please?
Sorry, how I determined what?
X and the Y.
Well, I didn't determine it. It was automatic from the Euclidean algorithm. I just started working the Euclidean algorithm backwards. Here's 7 as this minus this, right? So it's a multiple of 77 and a multiple of 14. But 14 is this difference. So here's my 77, and 14 is this minus this. And when I collect the terms, I get this. But 77 is this minus this. And when I collect the terms, I get the answer. So I didn't have to do anything. The Euclidean algorithm does it all. I mean, it required no thinking on my part. It was just an algorithm. It's automatic. It's like a computer executing a program.
I see it.
Right.
Thank you.
Right. So this, someone asked if this is being recorded. It is. Okay. Problem 2 is to prove that if R divides ST and R and S are relatively prime, then R divides T. So for the proof, we use two facts. First, if the greatest common divisor of R and S is 1, then there exist integers x and y such that Rx plus Sy is equal to 1. And if R divides ST, that means that ST is R times, let's say, Z for some integer Z. So if I take Rx plus Sy equals 1 and multiply by T, I get Rxt plus Sty equals T. Or let's say T equals this. Right? I just multiplied this by T. But St is Rz. So this is Rxt, and St is Rzy, which is R times Xt plus Zy. So R times this number is T. So therefore, R divides T. And that's the proof of Euclid's lemma. So if R divides a product of two integers and is relatively prime to 1, then it divides the other. Any questions about that? Yes, no? Okay. In problem 3, we're given integers a1 and a2 that are congruent to each other mod m, which means a1 is a2 plus mx for some x, for some integer x. And if b1 is congruent to b2 mod m, that means that b1 equals b2 plus my for some integer y. So if you multiply a1 times b1, that's a2 plus mx times b2 plus my. So let's actually multiply it. You get a2 b2 plus m a2y plus m b2x plus m squared xy. So a1 b1 is a2 b2 plus these three other terms, and I can factor an m out of it. I get a2y plus b2x plus mxy. So that means that a1 b1 is congruent to a2 b2 mod m, because the difference is divisible by m. And that's the whole proof. Questions about problems 2 or 3? So number 4, A, we want to solve a system of congruences. X congruent to 3 mod 5 and X congruent to 5 mod 6. And so by the Chinese remainder theorem, because 3 is congruent to 5, modulo the greatest common divisor of 5 and 6, which is 1, and 1 divides everything, we know there's a solution. And in fact, there is a unique solution modulo the least common multiple of 5 and 6, which is 30. So this tells us that the problem has a solution and we can find it. So if X is congruent to 3 mod 5, that means X is a number of the form 3 plus 5y. And then X congruent to 5 mod 6, this means 3 plus 5y is congruent to 5 mod 6, which means 5y is congruent to 2 mod 6. And we know this has a solution because 2 is divisible by the greatest common divisor of 5 and 6. We know this has a solution. And then we just look for it. If nothing else, you can just do it by trial and error. Plug in 0, 1, 2, 3, 4, and 5 for y until you find a solution. And this one solution is 5 congruent to 4 mod 6. Because 5 times 4 is 20. 20 minus 2 is 18, and 18 is 6 times 3. So y is a number of the form 4 plus 6z, and x, which is 3 plus 5y, is a number of the form 3 plus 5 times y is 4 plus 6z. This is 3 plus 5 times 4 was 23 plus 30z. So the solution of this pair of congruences is all x congruent to 23 mod 30. And you should always check 23 minus 3 is 20, which is 4 times 5. So 23 is congruent to 3 mod 5. And 23 minus 5 is 18, which is 3 times 6. So 23 is congruent to 5 mod 6. So 23 is the unique solution of this pair of congruences, mod 30. Okay. Any questions about this? Yes, no? Okay. What about part B? So for B, we have another system of congruences, 2x congruent to 1 mod 5, and 5x congruent to 1 mod 6. So again, we'd like to use the Chinese remainder theorem, but the Chinese remainder theorem only applies when the coefficient of x is 1. And here the coefficient of x is 2, and here the coefficient of x is 5. So to get it into that form, we have to solve each of these linear congruences. So we want to solve 2x congruent to 1 mod 5. This has a unique solution mod 5 because 2 and 5 are relatively prime. And it's easy to check that this is the same as x congruent to 3 mod 5. because 2 times 3 is 6, 6 minus 1 is 5. And we have to solve also the second congruence, 5x congruent to 1 mod 6. And 5 and 6 relatively prime means this has a unique solution mod 6. And you can check that x congruent to 5 mod 6 works, and so that's the only solution. So this system of congruences is equivalent to this system of congruences. But this is exactly part A of the problem. So therefore the solution, let's call this star of star, is the solution of this, which is all x congruent to 23 mod 30. So the system of congruences in part A has the same solution as the system of congruences in part B. Questions? Okay. What about number 5? In number 5, we have a permutation in S7. In standard form, it's 5, 4, 6, 7, 3, 1, 2. And if you write this as a product of cycles, let's see, 1 goes to 5, 5 goes to 3, 3 goes to 6, 6 goes back to 1. And then 2 goes to 4, 4 goes to 7, 7 goes back to 2. So this is the unique representation of this permutation as a product of disjoint cycles. Disjoint cycles commute, so I could also have written it in the opposite order, but that's still unique. Part B was to write this as a product of transpositions. And this you can do in a lot of ways. For example, 1, 5, 3, 6 is 1, 6, 1, 3, 1, 5. It's a product of these 3 transpositions. And you can check. 1 goes to 5, 5 goes to 1 goes to 3, 3 goes to 1 goes to 6, 6 goes to 1. And 2, 4, 7 is the product 2, 7, 4, 7. So this is one way to do it. Some people also did it as, so 1, 5, 3, 6. You could also write as 1, 5, 5, 3, 3, 6. Because this sends 1 to 5, 5 to 3, 3 to 6, 6 to 3 to 5 to 1. And 2, 4, 7 is 2, 4, 4, 7. And there are other ways to do it. So here we have product transpositions. What is sigma squared? You multiply sigma by itself. So when you multiply sigma by itself, that means you iterate sigma. It's the composite function. 1 goes to 5 and 5 goes to 3. So 1 ends up at 3. 2 goes to 4 and 4 goes to 7. 3 goes to 6 and 6 goes to 1. Let me separate this so it doesn't look like 12. This is a 1. There's the 2. 4 goes to 7 and 7 goes to 2. 7 goes to 2 and 2 goes to 4. Oops, that's right, but that's not what I wanted. The next one is 5 goes to 3 and 3 goes to 6. 6 goes to 1 and 1 goes to 5. 7 goes to 2 and 2 goes to 4. So this is sigma squared. And when you write it as a product of disjoint cycles, 1 goes to 3. And 3 goes back to 1. 2 goes to 7, goes to 4, goes back to 2. And 5 goes to 6 and 6 goes to 5. And finally, sigma inverse. What is that? Well, 6 goes to 1, so the inverse sends 1 back to 6. 2 goes to 4, so the inverse sends 4 to 2. 3 goes to 6, so the inverse sends 6 to 3. 4 goes to 7, so the inverse sends 7 to 4. 5 goes to 3, so the inverse sends 3 back to 5. 6 goes to 1. We already did that. Let's see. 7 goes to 2, so the inverse sends 2 back to 7. And 1 goes to 5, so the inverse sends 5 back to 1. So this is sigma inverse. And if you write this as a product of disjoint cycles, 1 goes to 6, 6 goes to 3, 3 goes to 5, 5 goes back to 1. Let's see, what about 2? 2 goes to 7, 7 goes to 4, 4 goes back to 2. That's problem 5. Questions about any of this? Number 6, we have two matrices. S is 0, -1, 1, 0, and T is 1, 1, 0, 1. So what is S squared? You multiply S by itself, you get -1, 0, 0, -1, or minus the identity. And T inverse, well, among other things, we have a rule for finding the inverse of a matrix. You interchange the diagonal elements, of course it's 1 and 1, and then you multiply the anti-diagonals by -1, you get -1, 0. So that's T inverse. What is ST? You multiply these matrices, you get 0, -1, 1, 1. And then we want ST cubed, so we have to first find ST squared. So that's 0, -1, 1, 1 times 0, -1, 1, 1. That's equal to -1, -1, 1, 0. And ST cubed is ST times ST squared. That's 0, -1, 1, 0 times ST squared -1, -1, 1, 0. That's equal to -1, 0. Let me just double check that I didn't make too many mistakes here. ST 0, -1, 1, 0, 0, -1. Sorry, ST 0, -1, 1, 0 times 1, 1, 0, 1. So it's 0, -1, 1, 1. So ST squared, I multiply this by itself, 0, -1, 1, 1 times 0, -1, 1, 1. So that's -1, -1, and 1, 0. So ST cubed is ST times ST squared, 0, -1, 1, 0 times minus 1, 1, 0. So I get minus 1, 0, and minus 1, minus 1. So that's not right. I'm pretty sure that's not right. So let me just see what I did wrong. Or maybe it is right, but
Professor,
yeah,
the ST is 0 minus 1, 1, 1, and you put 0 minus 1, 1, 0.
thank you.
Yeah.
Yeah, ST is 0 minus 1, 1, 1, right. So then I get, yeah, exactly. Minus 1, 0, 0, minus 1. That's what it is. Right? That's part A. Part B, prove by induction that t to the n is 1 n 0, 1 for all non-negative integers n. So first of all, t to the 0 is always the identity. That's 1, 0, 0, 1. So I have a 0 there. T to the first power is 1, 1, 0, 1, which is exactly this formula. So assume t to the n is 1 n 0, 1. Then t to the n plus 1 is t times t to the n. That's 1, 1, 0, 1 times 1 n 0, 1. When I do my matrix multiplication, I get 1 n plus 1, 0, 1, which is what I want to get. So if this statement is true for n, it's true for n plus 1. That's the proof. So it's true for all positive integers n. And then t to the m times t to the n, we just proved t to the m is 1 m 0, 1, and t to the n is 1 n 0, 1. When you multiply these, you get 1 m plus n 0, 1, which is t to the m plus n. So we just check that. Any questions about this? Okay. Number 7. Number 7 is to prove that the determinant is multiplicative. So if we have X is the matrix A, B, C, D, the determinant of X is AD minus BC. And if Y is E, F, G, H, the determinant of Y is EH minus FG. The matrix X times Y, you multiply, you get AE plus BG, AF plus BH, CE plus DG, CF plus DH. So the determinant of X times Y is this times this minus this times this. AE plus BG times CF plus DH minus AF plus BH times CE plus DG. And then you just multiply through and see what happens. So you distribute this across, you get ACEF plus ADEH plus BCFG plus BDGH minus this. So you get minus ACEF minus ADFG minus BCEH minus BDGH. And then there's some cancellation. These cancel. These cancel. So I'm left with these four terms. So here I have an AD times EH minus FG. And if I factor out a minus BC from this, I get EH minus FG. And if I factor out this, I get AD minus BC times EH minus FG. And those are my two determinants. This is the determinant of X times the determinant of Y. So this is a very important calculation, and it's important to do it a few times. And then the last problem, number 8, we define the commutator of two elements in a group as X inverse Y inverse X times Y. And we can say that this commutator is the identity if and only if, well, the commutator is this, X inverse Y inverse XY is the identity. If I multiply on the left by X, I get Y inverse XY equals X. If I multiply again on the left by Y, I get XY equals YX. So if and only if X and Y commute. And that's what I wanted to prove. Okay. Any questions about anything on the exam? No? Okay. So,
I'm sorry, Professor, I have a question.
yes, sorry. Can you speak up? It was hard to hear you.
Yeah. Is there any extra credit?
Any extra credit? Yeah, there
Yes.
was a lot of extra credit because there were, the exam was graded on the basis of 20, but there was a total of 24 points. So that's like if you multiply by 5, if you want to understand it in terms of 100, it meant that there were 120 points on a 100-point exam. So there are 20 points of extra credit on the exam. Yeah. So there was a lot of extra credit. Okay. Well, then what we're about to start is the main topic for this course, of which we've been looking at examples, and that is group theory. So we've looked at 3 important examples of groups. First, we had the integers, Z, and congruences modulo M. we looked at permutation groups. Sn, and we looked at the group of 2x2 matrices. For example, SL2Z, which is all the matrices A, B, C, D, where A, B, C, and D are integers, and the determinant AD minus BC is 1. So these are three very, very, very important examples of groups. And what we are now going to start to try to understand are the theory of groups. Okay. So we'll start with a few basic definitions. So we have a group G, which we're usually going to write multiplicatively. And then there's an easy translation, or eventually it becomes easy to translate every multiplicative property into an additive property. So let's recall, first of all, we have some words. A semigroup is a set with an associative multiplication. So there's some binary operation with the property that AB times C is A times BC for all A, B, and C in the semigroup G. And an element E in G is an identity if AE and EA equals A for all elements A in the semigroup. And we don't use this language very much, but what is called a monoid is a semigroup with an identity. So for example, the set of all integers n greater than or equal to 75 is a semigroup. Well, let me use multiplication. So the set of all integers n, let's say greater than or equal to 75, is a multiplicative semigroup. There's nothing special about 75, but if you take two numbers greater than or equal to 75, the product is greater than or equal to 75. The set of all integers n greater than or equal to 1 is a monoid, because this is not only closed under multiplication, but there's an identity element 1. So this is an example of a semigroup, and this is an example of a monoid. An element X in a monoid G is invertible if there's an element Y in G such that XY and YX equals the identity. And the object we're going to be studying basically until the end of the semester is groups. A group is a set, let's say G, such that, first of all, with a multiplication such that multiplication is associative. So G is a semigroup. There is an identity element, let's call it E, in the group. So G is also a monoid. And third, every element X in G is invertible. So for example, Q star, which is all non-zero fractions or non-zero rational numbers, is a multiplicative group. Of course, it's closed under multiplication. It contains 1, and the inverse of an element, X is 1 over X, is also a rational number. And SL2Z is also a group with this operation of matrix multiplication. Now, let A and B be subsets of G. We can multiply subsets. The product set AB is just the set of all elements of the form A times B, where A is in A and B is in B. And if A is contained in G and X is an element of G, then we have the left translate X times A. This is the product of the set consisting of just X and the set A. So this is everything of the form X times A, where A is in A. This is what is called the left translate. And we also have the right translate. AX is the product of these two sets. So this is everything of the form A times X, where A is in A. If G is abelian, then the left translate equals the right translate, because XA equals AX. If G is not abelian, then maybe XA is different from AX. That is, they can be different. They might be the same, but they can also be different. Okay. And the important case of a translate is when you have a subgroup. So that G be a group with identity element E, a subset H of G is a subgroup if, first of all, A is a group with the same multiplication as in G, and the identity is in A. So for example, if we take the group G equal the set, Q star, this is the non-zero rational numbers. And we take H to be Q star greater than 0. This is all rational numbers that are positive. This is a subgroup. H is a subgroup of G. It's not the whole thing. Like -1 is in G, but it's not in H. But the product of two positive numbers is positive and 1 is positive. So H is a subgroup, a proper subgroup of G. Okay. Here's another example. Suppose we take G to be the integers under addition. Suppose we take H to be 2Z, which is the even integers. This is a subgroup. The identity in G is 0, and 0 is even, so it's in H. The sum of two even numbers is even. The difference of two even numbers is even. So H is a subgroup of G. And in fact, for any m greater than or equal to 2, if you take the set of all multiples of m, this is a set of all numbers mx, x and z, this is another subgroup. So 3z, the set of all multiples of 3, is a subgroup. Okay. Any questions about this? So we now come to a very important definition. So if G is a group, H is subgroup, and X, any element of G, so the translate XH is called a left coset of H. So it's just this translation or this product set. XH is everything in the form X times little h for all H and H. So you're taking the subgroup H and multiplying it on the left by X, and that's called a left coset. And we let G/H this is the set of all left cosets of H. The set HX is called a right coset of H. So HX is the set consisting of what you get by multiplying all elements of the subgroup H on the right by X. And we let H/G be the set of all HX, X and G. So this is the set of all right cosets of H. And what is called the index of the subgroup H and G, which is denoted in square brackets G colon H, is the number of left cosets. of H and G. In other words, the cardinality of G mod H, that's what we mean by the index. Okay. Any questions about this? Okay. It's also, recall the definition of the order of a group. The order of a group G, which is denoted by G with absolute value signs around it, is the number of elements in G. It's just the size of G. So for example, if you have the multiplicative group consisting of just the numbers 1 and -1, this is a group, because it's closed under multiplication and every element has an inverse. The order of this group is 2. If you let G be the group consisting of the three numbers 1, -1/2 plus √3/2i, and -1/2 minus √3/2i. So in the complex plane, that's just these three numbers on the unit circle. This is an equilateral triangle. This group has order 3. This is a group. If you take the additive group of integers, the order is infinite because there are infinitely many integers. So let's look at some simple cosets. Suppose we take G to be the integers and H to be the even integers. So what is X plus H? That's X plus 2Z. So this is all numbers of the form X plus 2K, K any integer. So there are two possibilities. If X is even, an even number plus an even number, this just gives you all even numbers. So this is just 2Z. Sorry, this is if X even. And if X is odd, an odd number plus an even number is odd. This is all numbers of the form 2K plus 1, K and Z, which I can write as 1 plus 2Z. So if you take the even integers and you, as a subgroup of the integers, and what are the left cosets? Well, if you translate the even numbers by an even number, you just get back the even numbers. And if you translate the even numbers by an odd number, you just get back all the odd numbers. So the set of left cosets of 2Z is just the set of even numbers and the set of odd numbers. So the cardinality is 2. The set Z of integers is infinite. The subgroup 2Z of even integers is infinite, but there are only two cosets, 2Z and 1 plus 2Z. So even though this group is infinite and this subgroup is infinite, the number of left cosets is finite. In fact, it's just equal to 2. So it's really worth spending an hour just thinking about this one example, if you have to understand it. It's very, very, very fundamental. Let's look at Z mod 3Z. What are the cosets of 3Z? What is 3Z? This is all integers. It's all multiples of 3. Or if you like, it's all integers n, such that 3 divides n. That's what 3Z is. Suppose I take a number x equal 3 times L. What is the left coset or the coset x plus 3Z? This is all numbers of the form 3L plus 3K, where K is an integer. This is all numbers of the form 3 times L plus K, where K is an integer. But this is just a set of all integers divisible by 3. So this is 3Z. So if x is an integer that's divisible by 3, x plus 3z is just 3z. Suppose x is a number which leaves a remainder of 1 when you divide by 3. Then x plus 3z is 3l plus 1, that's x, plus everything of the form 3k. So this is everything of the form 3 times k plus l plus 1 for all k. But this is just a set of all integers, k. It's 3k plus 1, k and z, which I'll write as 3z plus 1. Okay. Sum of these two sets. And if x is 3l plus 2, x plus 3z is everything in the form 3l plus 2 plus 3k, k and z. And this is again just everything in the form 3k plus 2, k and z. So this is 3z plus 2. So this is all possible cosets, because you take the subgroup 3z, you translate it by an integer x. Every number is congruent to either 0, 1, or 2 mod 3. These are only 3 possibilities. And you only get 3 different cosets. So z mod 3z consists of the cosets 3z, 3z plus 1, and 3z plus 2. And so the index of the subgroup 3z and z is 3, because this set of left cosets contains exactly 3 cosets. Any questions about this? Okay. There's a very important, simple class of groups called finite cyclic groups. So suppose we let G consist of the following elements: E, which is going to be the identity, A squared, A cubed, all powers of some number A up to A to the n minus first power. So these are just symbols. And in this set, we define multiplication as follows. A to the I times A to the J, well, the two possibilities, it's going to be A to the I plus J if I plus J is no bigger than n minus 1. And it's going to be A to the I plus J minus n if I plus J is greater than or equal to n. So for example, if you take n equal to 3, G is a set with 3, oh, and also I should say E times A to the I and A to the I times E is equal to A to the I. This is going to be the identity. So suppose we take E, A, and A squared. So this is going to be a group with 3 elements. Here's the multiplication table. E times anything is the anything. A times A, this is A to the first power. 1 plus 1 is 2 is A squared. Oh, also, and also A to the 0 is E. A times A squared is A cubed. If I plus J equals n, then A to the I times A to the J is I plus J minus n is A to the 0 is the identity. So A to the n is the identity. So A times A squared is A cubed, which is the identity. A squared times A is A cubed, which is the identity. A squared times A squared, 2 plus 2 is 4. Subtract 3, you get 1, A to the first power. So this is the multiplication table for this group with 3 elements. And it's called cyclic because you can think of it as you have A multiplied by A, multiply again, multiply again, A to the n minus 1, multiplied by A, you get A to the n, but A to the n is E. So this is sort of a picture you might have in your head about what multiplication in a cyclic group looks like. So for example, suppose we take G, a cyclic group of order 6. So it has 6 elements, A squared, A cubed, A to the 4th, A to the 5th, and A to the 6th is the identity. And I claim that if I take H to be E, A squared, and A to the 4th, I claim this is a subgroup. Because it's closed under multiplication, these are this is A to even powers, so the sum is A to an even power. And every element has an inverse. A squared times A to the 4th is A to the 6th, which is E. And A to the 4th times A squared is A to the 6th, which is E. So the inverse of A squared is A to the 4th. The inverse of A to the 4th is A squared. So every element has an inverse. So the order of G is 6. The order of the subgroup H is 3. What are the cosets? So suppose I take the coset AH. So this is A times E, A squared, A to the 4th. So that's AE, AA squared, and AA to the 4th. This is a cubed, a to the fifth. This is the odd powers of a. In fact, if I take a cubed e, that's a cubed times this. That's a cubed, a to the fifth, a to the seventh. But notice a to the seventh is a times a to the sixth, which is a times e, which is a. So this is just a cubed, a to the fifth, and a. And in fact, you should check that AH and a cubed h and a to the fifth h are the same. It's the odd powers of a. And a squared h and a to the fourth h and EH is h. So there really are only two distinct cosets. So G mod h consists of the left coset h and the left coset AH. So the index of G and H is equal to 2. And they've taught you that 2 is 6 divided by 3. And 6 was the order of G. And 3 is the order of H. So for this finite group, we have this beautiful relation that the number of cosets of H and G is the order of G divided by the order of H. And this is a general phenomenon, which is one of the fundamental facts in group theory, and it is called Lagrange's theorem. So this is really important. Let G be a finite group. Let H be a subgroup of G. Then the index of G and H, that's the number of left cosets of H and G, is the order of G divided by the order of H. In the proof, what we're going to show is if you take the group G, you can partition it into left cosets. So we shall partition G into left cosets of H. So left coset looks like X times H. This is everything in the form XH, H and H. And we know always that the identity is in H. So X, which is X times E, is in the left coset. So every element is in a left coset. So G is the union of all the left cosets of a subgroup H. But of course, one element can be in many left cosets. And I claim the left cosets of H partition G. And the way I'm going to show that is I will show that if one left coset intersects another, then in fact they're equal. So if we have two left cosets, XH and YH, and the intersection is not empty, then XH equals YH. Okay. So I want to prove that if two left cosets have even one element in common, then they're the same. So proof. Let Z be something in the intersection of these two left cosets. That means there exist X1 in H and X2 in H such that Z, it's in this left coset, so it's XH1, and it's in this left coset, so it's also YH2. Let me repeat that on a clean piece of paper. So here I have my group G. Here I have a coset XH. Here I have a coset YH. And I'm assuming there's some element Z which is in both of them. So because Z is in XH, that means that there exists an element H1 in H with Z equal to XH1. And because Z is in YH, there exists an element H2 in H with Z equal to YH2. So therefore, XH1 equals YH2. And if I multiply on the right by H1 inverse, X is Y H2 H1 inverse. So let W be any element in XH. So W is equal to X times H for some H in H. So W, which is XH, but X is YH2 H1 inverse times H, which is Y times H2 H1 inverse H. And this is something that's in H, because it's a product of elements in H. So this is in the left coset YH. So this says that every element in XH is in YH. So XH is a subset of YH. But the argument also works in the opposite direction. Let U be in the left coset YH. So then U is YH prime for some H prime in H. Now, remember from this relation, if I multiply it on the right by H1 inverse, I get X is equal to this. If I multiplied on the right by H2 inverse, I would get Y is XH1 H2 inverse. So U, which is YH prime, I can write Y as XH1 H2 inverse H prime. This is X times an element of H. So this is in XH. So every element in the left coset YH is contained in the left coset XH. So I have XH contained in YH, YH contained in XH, If two sets have the property that each is contained in the other, then the sets are equal. So what I've shown you is that if you have XH and YH, and there's something that's common to them, so XH intersect YH not equal to the empty set, implies XH equals YH. So the left cosets XH are what we call pairwise disjoint. So you might have X1H, X2H, X3H, and so forth. You have all of these left cosets, and they have no elements in common. So they partition G. Now, if G is finite, then the number of left cosets is also finite. That means the index of H and G is finite. Call this R. This is the number of left cosets. So let G mod H consist of exactly these R left cosets, X1H, X2H, X3H, up to XR times H. So this is a partition of G. G is the union of these R sets. And because they're pairwise disjoint, the number of elements in G is the sum of the number of elements in each left coset. And I claim that all of these cosets have exactly the same number of elements. So I claim the cardinality of the left coset XH is the same as the cardinality of the subgroup H for all X and G. Now, what does it mean for two sets to have the same number of elements? And another word for the number of elements in a set is cardinality. So two sets have the same number of elements or the same cardinality if there exists a function f that's two sets, let's say X and Y. From X to Y, that is 1 to 1 and on to. That's the definition of two sets having the same number of elements. You have X and you have Y, and you have some 1-to-1 correspondence between the elements of X and the elements of Y. That's the definition of two sets having the same number of elements. So define a function f from H to xh as follows: f of h equals x times h. So this is a function from the subgroup H to the left coset xh. And f of h1 equals f of h2 if and only if xh1 equals xh2. And if you multiply on the left by x inverse, h1 equals h2. So f is 1-to-1. And if I take f of the element x inverse h, that's x times x inverse h. Sorry. So first of all, f of x is onto, because everything in xh in this left coset is xh. For some element h, f of h equals xh. This function is onto. This says it's 1-to-1. So f is a 1-to-1 and onto function. So therefore, the cardinality of x equals the cardinality of xh for all x. So when I had obtained this result that the cardinality of G is partitioned into a finite number R of cosets, R is the index. Each of these left cosets, they're pairwise disjoint and their union is G, so the size of G is just the sum of all these left cosets. But every left coset has exactly cardinality of H elements. So we have the index of G in H is equal to R. So G is the union of R pairwise disjoint left cosets. So the cardinality of G is the cardinality the sum of the sizes of these cosets, but every left coset has cardinality H. So I'm just adding size of H to itself R times. This is R times the cardinality of H. So the cardinality of G divided by the cardinality of H is R, which is the index of H and G. This is Lagrange's theorem. So this is truly one of the most important theorems in algebra. For a finite group G and for a subgroup H, the index, the number of left cosets, you can also write it as the cardinality of this set of left cosets, is the cardinality of G divided by the cardinality of H. This is really, really important. So I have some notes that I may have posted already, but in any case, I'm going to revise them and clean them up a little bit and post them later today. So there will be a chapter on group theory available on Blackboard this afternoon. And the more time you spend studying it, the more you'll know. This is really the fundamental stuff in this course, is this the theorems in elementary group theory. Any questions about this? Okay, so we're done for today. I'll stay on Zoom a little bit after class right now. So if you have any questions about your exam or anything else, I'm available. It's just like an office hour. Otherwise, we're done.